Robert and I started Planetary Utilities with the goal to bring our lessons learned from our time at JPL together with the new capabilities that are emerging in the space industry, in the new space industry, to the market. And so what we came up with is a modular system to build large spacecraft, basically. So in this system, we have a backbone, and then on both sides of this backbone, we attach modules. And the key differentiator here is that the subsystems of the spacecraft are also contained in the modules. So it allows for a very flexible way to design different space missions. And the interfaces between the modules and the backbone are standardized so that they become exchangeable and can be predefined. And that has a lot of advantages. A few of those to mention is that now we can test the modules individually, and by that parallelize the development process for space missions. So a modular concept or modular concepts have been around in the space industry since a long time. However, only the new launch vehicles, predominantly the heavy lift vehicles that are on the horizon right now, are changing the economics of space in a way that the modularity overhead will become economically advantageous. So now it's cheap enough to launch more connectors and interfaces into space and get the advantage of being able to standardize and commoditize systems and subsystems, instruments, and payloads in general. And then down the line, also exchange modules in space, and also automate the processes for testing. So that's the concept behind all of this. So just to give an impression of the size, the modules are 1 cubic meter, 1 kilowatt, 1 ton. So that's just to give you an idea of how big the system is. We have 14 modules on a single backbone, so it's about a 10 to 12 ton spacecraft. And so the goal here is to build a shared infrastructure where these services like power, attitude, thermal control can be exchanged in space and can be procured like services on a service-based platform. And then the applications of observation or transportation and manufacturing are built upon that platform. Here is an example mission profile. These are 3 backbones and then 4 power units. We have a 100 kilowatt power system, and with a 4 Newton electric thruster, we can get to the moon in a year and a half. And out of 40 tons total spacecraft mass, we can get 20 tons of payload to the moon. So this will be the lowest cost option to go to the moon. It takes a little while, but just one example of what's possible with such a platform. But to engineer this system, we've built out a pipeline. For instance, to generate these models, we're building them in NVIDIA's Omniverse, in this case. And so we have been, from the get-go, focused on how to integrate the different system models into our software tool. So what we can see here, and Tim already showed some screenshots from the Starforge software, is a view where we have the AI chat on the left side, and then on the right side, we see a thermal model of our system. And so the operator here asks the AI to create a new backbone, add some power systems, and in the background, the logic of the engineering model gets triggered from the AI, and so the model gets built up, and it's not just the thermal model in this case, but it's also a SysML model that gets built up that is all-encompassing and includes many more aspects of the system. And so here we can see we are adding solar panels to the system and are adding a few more modules. The last one is a thermal module to control the temperature on the spacecraft. And now we are also asking the AI to deploy the radiator, for instance, on this module. And so we can also interact with the design. We have also integrated the CAD information in the SysML model. As Sandy showed earlier, SysML v2 has great provisions to integrate the CAD information. Not the details of components, but the information about the assembly level structures and the coordinates of the modules in this case. And so what we saw here was an export to Onshape, which is a browser-based CAD tool. And then we can also export it into the Omniverse to get a graphical view and a rendering of the spacecraft. And lastly, to evaluate the design in orbit and to simulate the systems, we have integrated with Cedero, which is also a browser-based tool that has similar functions as STK. And here we can see that we can simulate the electrical flow through the system and other properties of the spacecraft as it orbits the Earth. So from a single model with this modular architecture, we can now create a system where we can put together various spacecraft, look at them in CAD, look at them in Omniverse, and also look at their performance if we specify an orbit directly in one tool, in one environment. So that was the software side that we had engineered for our system. And on the hardware side, we started building a prototype, and this was our first prototype built up. This was actually in my front yard, and it's a 10-foot tall structure with 3 of these modules. And we put that prototype in my Sprinter van, and we brought it over to Austin, where we showed it at the last year's Fed Supernova conference. And the response from the industry was quite positive. A lot of people came to us and said, I always thought space systems should look like this. So that was a quite positive surprise. In January of this year, then, my town, Altadena, here in California, got hit by the Eaton fire. And so my house burned down, which was our office at the time. And after coming back from the conference, we had put this prototype in our garage. And the day before the fire, after half a year, we had set it up again in outside of the garage. And that's why it survived. And when we came there and saw that devastation from the fire, this standing piece of hardware was, I think, our biggest inspiration to keep going and bring this idea and make it a reality. So now it's in our new office in Monrovia, also Los Angeles area, where we are now headquartered, and it still has some marks from the fire on there. So this is our little symbol of resilience in the face of adversity. But yeah, to shifting the space industry into a new paradigm requires us to rethink the engineering ecosystem. And luckily, we have a lot of experience to draw from, because JPL has been spearheading model-based engineering since more than 10 years and has many experiments, pilots, prototypes that have been used on actual space missions. And from JPL emerged the Dragon architecture of continuously refining digital twins along the product life cycle. And so this Dragon architecture is kind of a blueprint that is very generic for systems design. And OpenMBE, which Chris will be talking about after this talk, is the foundation for this architecture. So with Starforge, we are sitting on the shoulder of giants, basically. The goal is here to build a platform and establish SysML v2 really as a platform technology, so that it's open for all of us and that we can work together as we wish. And so our Starforge platform is built upon OpenMBE as the backbone for storing models and evolving basically the center of the digital thread, basically. And then Seaside from Sensimetry is definitely one of the most advanced SysML v2 implementations, and it's very performant. So we chose that as the SysML v2 interpreter. And then Tom Sawyer software provides an excellent visualization of graphs, and so we integrated that into the platform as well. The idea here is that the integrations of other tools, as they are part of the engineering lifecycle, can be accomplished on the basis of this open source project, so that people can integrate their own data as they need and share these integrations also among the industry. And then on top, Starforge, we are building the tools to create a AI native design environment that uses the design language framework to create these system models that provide this executability that I showed earlier. So the framework here has a lot more parts to it. This is from a paper from JPL, what's already integrated with the OpenMBE architecture. And Chris and Doris will show a little bit more about that. And then our part is integrating and creating a showcase with our modular space system for this architecture. In terms of the AI, Tim has already mentioned this earlier, and also Sandy has brought it up. So for using AI in an engineering context, it's really important to understand that a lot of engineering disciplines do not have the benefit of programming and languages as Python, where huge swaths of code are open source available. And so we cannot train these AI large language models. And so we need to engineer the knowledge that we need them to include in a specific task. And this is mostly done through agents. And so our software has a provision for creating an agentic framework, basically, where you can train your own agent and add your own information to the system as you need it, and also use other agents that are already present. So to conclude, Starforge is an AI co-pilot that understands engineering models. Since engineering data is often scattered in different tools, formats, and models, Starforge is built to bring these engineering data together. It reads the system's models, it reasons across disciplines, and produces combined results that you can work with. So it's basically building a platform for bringing all that information together so that we can use AI and leverage AI in a way that it helps us to build our systems faster and better. And it's not here to replace you, but it's basically here to bring your engineering onto a next level. And the easiest concept for that is basically to have a conversational digital twin where you can ask, what's the current mass of the system? And then it can respond. The system mass is 24.7 tons. But it doesn't do so in an LLM way where it just makes up facts, but it actually does so in a traceable way where the underlying model is based on a SysML model, and you can trace that information back to where it came from. But you can also use it to interact with your engineering tools. So for instance, if you want to generate a visualization, you can ask the agent to do that. Or if you want to see the latest CAD model of a configuration, you can ask the agent to do that. Or if you want to see a thermal model, you can ask the agent to do that. So let me go over and start showing a demo. I think I need to start sharing my screen. This one. All right. Can everybody see my screen?
Yes.
Yep, we see it.
Thank you. All right, so let's go. So here I can start and say, create a new nexus. And over here, we have the thermal view of the system. So it shows me the thermal model. Maybe I'll have to reload the page here. Yeah. So this is the model now of our backbone. And now I can say, please add 2 power units. I want to build a spacecraft with a lot of power, so I'm going to add 2 of those. I also want to see the solar panels, so I say, please add the solar panels. So what's happening in the background is that we have a model of our system, and the AI knows how to interface with it. Please add 1 battery unit. And so as we're building up our system, we can add the different subsystems for the spacecraft. So we're also going to need please add attitude control unit. And we're going to need a communication unit. And now we want to have a transporter unit so that we can actually do something. So this is basically the way the system is architected with these predefined interfaces. Now we get the benefit to easily swap in modules and add them to the system. And we can also, in case, for instance, we're missing a subsystem, so please also add 1 thermal unit. So now we have all the subsystems covered, and we can also interact with the system model. So if I have a thermal unit here and it has a radiator here, and now I want to see that radiator being deployed, so I can also say, please deploy the radiator on this thermal unit. And one of the main things that the AI does for us is that it creates a simplified accessibility layer to these engineering models. So I don't need to exactly know how to control this radiator or how to add these units. because I have an AI and the AI can also give me instructions on how to do things, it's a little easier to actually interface with the system, as long as I understand the main building blocks of a space system in this case and know what the subsystems are. The AI is here to help me create these models and use them. Okay, we want to add 2 more transporters. Okay, and so now we have built up this system model, and at the same time on the back end, we have built up this SysML v2 representation of the system. So we can see all our models specified here, and here we can see the geometric coordinates of the individual modules in this view, and we can also look at this not just in the view of a simplified thermal model here, but we can also look at this in Tom Sawyer here as we load in this model. We can, for instance, search for our attitude control. Let's search for the power unit. So here we can see the part definitions that we just created. And here is a representation of the system where we can see all the different modules that are attached to this Nexus backbone. Here are the transporter units and the power units. And so we can see that we're using the design language interface to create the system model in this case, but then we also have the SysML model in the background that creates a clearly defined deterministic model of our system. We can now, since we have the geometry information stored in this SysML model here, we can now also ask the system, please export this to Onshape. So Onshape is the browser-based CAD from PTC, and it's now starting the export where it creates a new model in Onshape, and it provides us a link here. So if we click on this link, we can watch how the geometry model is built up as the CAD system, through its API, is entering all the different modules and then placing them in the right location. So this is the kind of integrations that we see really bringing SysML v2 to a whole new level. Sandy mentioned it earlier that we don't want to use SysML as a geometry or a CAD system, but for system architectures, if, for instance, we pull just the assembly information into the system model, we can already have a lot of integration and a lot of functionality working as we have that information in the system model available. For instance, in our case, we are using it to generate thermal simulations and high definition renderings at the same time that we generate these CAD models. And it gives us the ability to create new system designs on the architectural level, but then look into the details of the different engineering disciplines. So we're going to let this tool here finish its work. So we can see here we have all the engineering detail now available. We see all the interfaces that are present in this model, and we can look if there's any conflicts And that way we just get a completely new understanding of our architecture, because we can execute it in all these different engineering domains. So if we go back here, we can also ask the model to export the model to Omniverse. So Omniverse is NVIDIA's 3D rendering tool. And what we have done is we have created a, it's already there. So we have created a container that can visualize these Omniverse models. And so in this case, this model gets rendered in an orbit around Earth. But these integrations are more to be seen as a more generic tool suite. It's not just for our modular space system, but we can also work with drones or other systems. It's really a general systems tool. Besides Omniverse for our space systems, what's also important is the orbit simulations. And so if we export this model to Cedaro, then we can start and explore this. We have this over here in this tab. Need to analyze this use case, and we have different systems in here. So Cedaro is a browser-based SDK, if you will. It allows for mission analysis. And so we can see here we have this spacecraft configuration, again, in an orbit. And the different subsystems are represented in that SysML model. So we bring that information over here. And now we can look, for instance, for the power subsystem. If we go over here, we can look at the different aspects. For instance, the flow of the electrical power. We can see how much electricity is generated on the solar panels, and who is the consumer at a given point in time. So we can see this view of the power bus here, for instance, and it's all integrated in one tool. And the goal here really is to give you all the different engineering views and dimensions at your fingertips, integrated with an AI, so that you can start reasoning and can start looking for system aspects across the different disciplines, and can really start leveraging that knowledge that is there and that we now have the power to connect. So our goal is really to empower the engineer and allow people to operate more on the systems level, on the architecture level, so that we can create better designs. All right. So that concludes the demo. I'll switch back to the slides over here. So yeah, we have this system view where we can see the SysML together with Tom Sawyer. But that's only one view of the system. We can add the different physics aspects. And as we create these different views, we have the SysML model in the background. We're not pulling all the information of the different engineering disciplines into the SysML model, but we are using it to pull in the information that is used across the tools. And that's really where the architecting and the engineering happens. So building a platform like this, for instance, where you can flexibly create new space missions, is really about defining architectures that allow you to make these changes, for instance, swapping out modules and having all that information that you need to do that in the systems model. The same with the view in the Sidero model, where it's basically much more about the behavioral aspect than about the structural aspect of the space mission. And so this is really why SysML v2 is the tool to go to, because there are simply no real tools in the engineering landscape that combine these two aspects. And so having behavioral aspects and all the structural and mechanical aspects in one model, that's really where the SysML v2 shines. And so in this SysML model, we can represent, for instance, the power system architecture. So when a new power module gets added, it establishes the power bus, and then the second power module, for instance, becomes a part of that power system. So there are certain rules that we need to implement in order to get a functioning system based on the modules that we're adding. But SysML provides us a platform where we can implement these rules and create these design languages so that we can have that logic, not just in the heads of the engineers, but now reflected in code and have it re-executable. The same with the CAD view. As I mentioned, the main thing that we're pulling up into the system level here is the architecture, so where the interfaces are located and how an assembly is achieved. And that, again, is really crucial information that we can reuse in multiple models. And so pulling it into the SysML is really valuable. One other model where exactly the same information is used is, for instance, this high definition rendering model. The individual module level representations are created manually, but the system level models are generated on the fly as we swap out modules. And this is really important. For instance, if we think about a future where we have a robotic modular space system, and we want to swap one of these modules, a location of these modules, and we want to put it from one location on the platform to another. We actually had exactly that use case on a mission at JPL EMIT, where we were receiving our module out of the trunk of the Dragon capsule and plugging it into the payload bay on the American module on the ISS. And the driving thermal use case for our system was that transfer period when the robot picked that module up and it was unpowered for a period of 6 hours. And so being able to generate these thermal simulations and a visualization of that operation, and then look at all the different options for how that transfer could happen, at which orbit, at which time in the orbit. That's really what we need to get truly robotic space missions. So those are aspects of our tool that are really addressing the pain points and shortcomings of the space industry right now. Yeah, so I think we have one more part of the slide deck here where we want to address the V1 to V2 migration, and I'll let Robert take the stage here.
Yeah, so here are two more cherries about V1 to V2 migration that kind of the sidekick of Starforge. So we take a slightly different approach here. Instead of like a formal one-to-one transformation, we use an AI-driven migration where we use queries to extract the relevant V1 elements, right? So you build up a set of queries, the things you want to extract, and then we transform that to V2. Can go to the next slide.
The confirmation stuff is different. Right?
There's some open mic, I think. Could you mute it, please?
Is this the slide you want, Robert?
Yes. So there's Can you? You're not full screen.
Has somebody got a
Yeah,
hot
there you
mic?
Yeah, there's an open mic. Can you mute
Yeah,
that?
I think it was
Sorry.
Sandy. Sandy, mute your mic.
It's not me. I've been muted.
Oh, it looked like it was coming from you. Sorry.
No, it was Bassett.
Okay, there we go. So that's an example where we query a SysML v1 model. That's the OMG hybrid standard hybrid SUV model, and we query it for a little bit of extension, adding specializations to the hybrid SUV. So you can interact and chat with your v1 model and say, okay, give me all the requirements related to a certain block, or give me all the requirements that are satisfied by a certain block, and so on. And in this example is show me all the specializations of the hybrid SUV, and it finds 3 specializations. And then you can transform that into a V2 model and build up like that your V2 model, extracting it for the relevant parts that you would like to have instead of having a full migration. It's a different approach that has its use cases. Another cherry is an initial capability for state machine-based behavior. Go one slide back.
Sorry, up
To the first one. Here, it's too fast.
Yep.
One more, this one, yeah, and run and play that. Yeah. So it's also integrated in Starforge, so you can specify your state machine in SysML v2. It uses the W3C as the XML standard for state machines and C-side underneath to transform it and then to execute it and render it. But it can also be integrated with other things like Cedar and co-simulations. If you go to the next slide. Right. So here you see a co-simulation where there is a Cedar model with different operational modes, imaging, cross-link, and forward. And you drive basically the simulation, the co-simulation from your Jupyter notebook. You can inject signals, you can do your state transitions, and the state machine is defined in SysML v2. And then you co-simulate your SysML v2 state machine and the vehicle pointing modes in Cedar or satellite. And I think that concludes our presentation.